this computer. Welcome again. Recurrent neural networks, MMI711, sequence models and multimedia, and this week's subject is recurrent neural networks. What I'm going to do is I'm going to make a very gentle introduction to recurrent neural networks. So this is not going to be an introduction to you. You already know briefly about recurrent neural networks because in the introductory level course, I am sure you had some sort of introduction to the subject. But because of the nature of the introductory level deep learning courses, usually that introduction to recurrent neural networks is not sufficient. So I'm going to do my best today to make another gentle introduction, to remind you what it was and to provide maybe more information about what the big picture is, because recurrent neural networks, when they were first invented, promised the world to the society. Then we have realized, and the scientific field realized, that it is not easy to make them work. Okay, let's begin. So this week, a brief history of artificial neural networks versus RNNs, and an introduction to the concept of RNN, the feedback, what makes it different from an ANN. We'll talk about the vanilla RNN, what is unrolling in time. I'm going to talk about briefly RNN input-output types, because RNNs are defined by how their input and output sequences are modeled, actually. Then I'm going to talk about different derivatives of vanilla RNNs, and I'm going to focus on one of them, actually one of the famous ones, which is called the Hopfield network. Okay, so this will be the gentler introduction we are going to do this week. So it all starts, guys, let me just move this here. Actually, if you look at the history of neural networks, this is one of the guys who kind of, one of the first thinkers of it, Ivanenko. He came up with this idea. When you see this formula, I'm sure you understand it. What he was trying to do is, in his head, he said that using different order polynomials, we can represent functions. And actually, he worked on the mathematical proofs of it. He did not prove that we could represent any function in this way, because that's another paper that I'm going to be talking about. But he was one of the guys who came up with an idea of a simple multi-layer perceptron of polynomial activation functions. Be careful, polynomial activation functions. The idea of activation functions evolved in time. So that's why he's considered one of the fathers of deep learning. But the idea he proposes to us, the polynomial-based neural networks, we don't use it much because we have better functions and better activation functions. So let's continue. What happened next in 60s and 70s was the idea of backpropagation being popular. Guys, this is very important because before the 50s, if you look at the history of mathematics, it was all theoretical. I mean, in the 19th century in Russia, there are very good studies. In the early 20th century, there are very important studies, but they are theoretical. What I mean by theoretical is the designs were not compatible with computation hardware because there were no computation hardware. As the computation hardware started to getting invented with the 50s, people in the mathematics field, especially working on discrete mathematics, just looked at the computation devices. Okay, there are these computation devices. Well, we could make use of them, but some of the formulas, some of the theoretical stuff we work on are so theoretical that it is impossible to implement them. It requires incredible amounts of memory, for example. You need to just keep a lot of values in mind. And starting with 60s, mathematicians started to come up with ideas which are more compatible with the hardware. And actually, backpropagation in computational graphs are actually one of the early ideas of mathematical functions being more applicable to computer hardware. Because you all know that backpropagation today, because you have taken an introductory level course to deep learning, is actually a way of efficiently training a computational graph. By efficiently, I mean efficiency in memory and computation. You do every layer one by one. So this was the first steps of artificial intelligence, because we cannot think of artificial intelligence out of computational hardware implementation. And actually, funny thing is, in 1970, this guy's Linnan, I cannot read it, Linanma. He's from Finland, I guess, Finland, yes. As far as I remember, he's from Finland. His master thesis, guys, most of you are doing master thesis and PhD thesis. He did apply backpropagation to neural networks. He thought the idea was backpropagation was invented from optimization and control engineering by then. He said that we could apply it to neural networks. So it was like a master thesis. I mean, it's an easy idea, but just imagining that it could work on neural networks is a nice thing to do in your master thesis. And actually, as the time evolved to the 80s, this idea was being implemented to different type of graphs. So the idea of automatic differentiation in graphs evolved. So at that point, people had better hardware in the 80s. So we could really talk about artificial intelligence. It was a fact. It was in the movies. It was in the world. So we could do automatic differentiation in computational graphs. And if we could create computational graphs, well, we could train them. We could apply optimization with limited hardware efficiently. Okay. So in the 90s, actually, this is a bit more later than that, the pioneers of RNNs, and they applied backpropagation through time for RNNs. Backpropagation through time. Maybe this is the first time you're hearing it, or if you've checked Coursera's course from Andrew Evangi, you've heard about it. We're going to cover it. Backpropagation in a computational graph, you know what it is. Backpropagation through time is a concept that we're going to cover specifically for recurrent neural networks in the following slides. So people talk about the AI winter a lot. Actually, in the growth of AI, we had two AI winters. One was the late 70s and the other one the late 80s, early 90s. In these periods, the focus of the scientific world, got farther from AI because it was like a hype, and it grew, and it was like a hype. And in these AI winters, frankly, we had some of the most important papers. For example, LSTM was somewhere around here. LSTM, nobody cared. The use of LSTM is, predominantly applied in these times. However, it was invented here. So it is like when you invent something in AI, specifically recurrent neural networks, if it hit the AI winter, nobody would have cared. And that happened actually. And actually the funny thing is, so this is a nice thing I've taken from a blog from Milton. He's a famous guy. So for example, another idea, Hopfield nets, which is an important idea today because it's one of the early ideas of associative memory. What is an associative memory? Neural network, a memory-based neural network I'm going to talk about. It is again, came up during one of the AI winters. So you can come up with an AI idea, which the society won't accept, the scientific society, but it might get very important in time. And actually, the funny thing is, during the first hype of AI, deep learning, around 2012, 2013, 2014, there were very important people in the AI society that thought that this was also a hype. Another AI winter was going to come, but apparently they were wrong, guys. The exponential growth continues. Actually, it is more than exponential. I sometimes think that the hype on AI today is like super exponential. It is everybody around me, my colleagues from the architecture department or other departments, they're calling me and telling me, can I watch your courses? We have to. So deep learning is like becoming one of the fundamental courses of engineering and the more mathematical sciences. Okay, is AI winter coming? No, I don't think so. Okay, so this was like a brief history. So in 1989, actually, one of the important papers come by Hornick et al. What they did was, they mathematically proved that when you have multiple layers, you can allow neural networks to theoretically implement any function. Any function. I mean, they proved that it is XOR, and by proving that they could implement XOR, it meant any function mathematically, because XOR was already proved to implement any function. And they had this paper, multi-layer feed-forward neural networks are universal approximators. And actually, recurrent neural networks, with their ability to hold a history, to hold an associative memory, are universal approximators as well. You can approximate the universe with a vanilla RNN. However, if you can train it or not, I'm not sure. So these RNNs, recurrent neural networks, with their additional ability to hold memory, in addition to feed-forward neural networks, compared to feed-forward networks, do have an incredible capacity, infinite capacity. But the problem is about training them. And as you've seen in the previous slides, the history of inventions related to neural networks and recurrent neural networks are all related to how to train them better and more efficiently. And this continues, guys. And it's going to continue in the following weeks as well. We're going to learn recurrent neural networks, the vanilla RNN, and we're going to learn that we cannot train vanilla RNNs properly. And there's a newer structure called LSTM. It is better than RNN because it is handcraftedly designed to be better trained. So I hope this gives you a small perspective. So before I finish the history, because I like the history, because I see the history, understanding the history of a course like the literature survey. If you don't understand the literature survey of a scientific field, it is impossible for you to make any contribution. You'll be just repeating what people have already done. So that's why always keep an eye on the history, because history of science is actually you doing literature survey. Anyways, my final slide about the history. In 82, J.J. Hopfield came up with this Hopfield network. We're going to talk about it today. But more importantly, in 86, this Rumerhalt was the first author. They come up with the idea of general RNNs. And they said that general RNN has the capacity to emulate the universe. And they were right. And actually, funny thing is, the second author of this paper is Hinton. Hinton is everywhere, guys. I mean, look at the last 50 years of the most important papers of AI. He's there. He's there. He's either, I don't know, a lecturer or a postdoc or a professor or the godfather of deep learning. Okay. Okay, check this paper. I mean, the name of the paper is, let me remember the name of the paper, because it was so generic that it was surprising. Yes, learning representations by backpropagating errors. I mean, it's so generic. I mean, the first response you would give to such a title is, of course, but they were the guys who just implemented this idea to networks with feedback and shown that, well, this is the way to do it. Okay, so this is like more like history. So I'm so sorry. So let us begin. So you know where you are in history now. I'm going to stop history here because at this point, we know in history, you know why RNNs, the idea of a feedback is important. So what that feedback is all about. I'm going to remind you the mathematical definitions. And those simple mathematical definitions will make a lot of sense actually. So first, this is a standard feed-forward neural network, guys. It's also called the artificial neural network or fully connected layers. Some call it the dense layers. In some libraries of Python, they are called the linear layers. Doesn't matter. What you do is you have an input layer with nodes. There are some values. There's an interconnection between each node of one layer to each node of the next layer. Okay. And you have multiple layers, which are called hidden layers, because we don't understand the activation, we don't necessarily understand the activation in the hidden layers. And in the end, you have an output layer. If the output is a single value, you have a single node at the output layer. So this is a very simple depiction of an ANN. And if you remember, this single node is usually called a perceptron. I mean, perceptron is a very limited definition because it's not usually, we call it nodes. Perceptron is a specific type of node. However, I mean, out of conventional usage, it's usually called a perceptron. And that's why these networks have also another name in addition to these, which are called the multilayer perceptrons, MLPs. So don't get fooled when you see a multilayer perceptron, artificial neural network, fully connected layer, dense layer, linear layer, all the same. Okay. So inside a perceptron, inside a node, what you basically do is three things. You know this: weigh, accumulate, and activate. this is like interpretation of our neural cells in our brain. So we have so many connections and so many impulses came from different sources. We weight them, and using some weights, predetermined weights. These are numbers in your artificial neural network. These are some chemical substances in your brain. You sum them, you add a bias. Some neurons have biases because maybe that neuron is very important. And in the end, you use a function. You just feed that value, that sum value, to a function, which is nonlinear. This function being nonlinear is very important. You should have learned this in the introductory level deep learning course. It has to be nonlinear so that, speaking in terms of machine learning, when you create a decision function in a hyperspace of features or input dimensions, you have to create some nonlinear surfaces. So this nonlinear function being nonlinear actually allows you to create nonlinear decision surfaces. Because if you don't have a nonlinear function, this network here becomes a linear system of equations. And in a linear system of equations, no matter how many layers you have, it's actually matrix multiplication. And in the end of a matrix multiplication, a multi-matrix multiplication, you end up with a linear system, which will create a linear discriminative surface. A linear discriminative surface in a multidimensional space is a hyperplane, so-called hyperplane, and it will only allow you to make certain types of classifications. However, the decisions we make as intelligent beings are highly nonlinear. And when we are trying to understand different features, actually the relations we come up with within those features are highly complex. That's what the artificial intelligence is. I mean, these are the subjects of the introductory level deep learning course. I'm also giving an introductory deep learning course this semester, you know, guys, in Wednesday. And in Wednesday, I'm talking about these subjects. So this was the subject of the previous course. So what is this RNN all about? You remember that FNN is simply a network of weighted inputs and nonlinear activations. So these layers, so this is a single layer, the input, the nodes, and the output of the layer. We have these 3 nodes in this layer. We construct with different deep layers, we construct deep networks. What we have is, actually, we have a simple recurrency here. Recurrency is a feedback. So this is the recurrent neural network, this is the feedforward neural network. As you can see, this is the only difference, the feedback connection. But that feedback connection makes an extremely important difference, guys. It creates the states and the memory. This makes this network a finite state machine. This guy is not a finite state machine. This guy is a finite state machine, mathematically speaking, just because of this recurrent neural network. Okay. So by feedback, we mean a connection from the output of the perceptron to itself. So the output of the perceptron is feeding itself, okay? What does this mathematically mean? So what I'm going to show you, the meaning of mathematics of feedforward neural networks is, I'm going to remind you the mathematics of a single layer, the linear layer. You have the input, which is x, a vector of n. Not necessarily true, but in this example it is. You just multiply it with a matrix because you have multiple connections. So if you want to talk about only this perceptron, it will be this pinkish reddish formula. So xn times 1 row of this matrix plus the bias of this node. So if you want to represent this single multiplication to the entire system, you don't use the row of the matrix, you use a complete matrix and the complete biases. That's why the biases equals to the number of the output nodes, and the matrix is output nodes times the input nodes, okay, times n. And G being the activation function, which we think to be nonlinear. So this was the feedforward neural network. What is the RNN? We have the additional, so we have every formula the same, but we have an additional connection. But one more difference, I called this output Y because for a feedforward neural network, it was the actual output. But in the RNN case, I'm not going to call it the output. I'm going to call it the states. So I'm not going to name this Y. I'm going to name this A. Or in some conventions, they name it H as well. I'm going to use the convention A. So how does the formula change? Very simple, actually. So, so this was the corresponding feedback added architecture. And I called this A because I called this states. So what about an output? If I needed an output, I will have to add a feed-forward linear layer to it. But I'm not going to add it for now. I'm going to focus on this part only, this part only. And if I focus on that part only, remember what the network was. A matrix multiplication times the input. But input changed. Input is not X only now. Input has A as well. So the input is now X and A concatenated. That's why the size of the matrix also changes. Is not there any bias? I didn't put the bias in the formula in this page just for simplicity. Of course there is bias, but to make the formula simple, and I mean to depict the formula simple, that's why I did it. So what changes is this, guys. So the matrix just grew, and the input layer is concatenated. And this is the next A. As you can see, this was the previous A and the next A. As you can see, I have created states. It looks like a finite state automata now because I can create states out of states. So it's a sequential machine now. That's why RNNs are used for sequence modeling. I can, if I want to, create an output using a linear layer out of the states. Actually, it is how it's done. If you have ever worked on an RNN in your deep neural network practices, you've always seen that after an RNN or after an LSTM, there's a linear layer to make the decision. So what we should first understand is when we make an FNN, when we transform an FNN to an RNN by this recurrent connection, we change the output of the network to be a state instead of an output. So this is the states, they are going to evolve. So if you need an output, which is the decision, then you will need another layer. That's the conventional usage of a vanilla RNN. And actually, when you hear a vanilla RNN, this is the core RNN. And the entire system is actually the vanilla RNN. And as the number of nodes increase in this vanilla RNN, this architecture, guys, believe it or not, is capable, has the capacity to emulate the universe. I'm not joking, the universe. I mean, of course, I'm imagining the universe as a deterministic system, not a stochastic system. I'm not doing quantum mechanics right now. If the universe is a deterministic system of events, then you can, well, maybe I shouldn't have said universe, you can emulate any level of deterministic system, any automata. Good. So, and this part being the output. So this is the vanilla RNN, the formula of the vanilla RNN. So if I get to the general formula with the biases, so this is the formula. Since we have in a vanilla RNN two parts, the core and the output, what I need is two separate formulas. The first one, creating the states, using the previous state, concatenating it with the output, input, I'm sorry, X, because input is going to change at each step. And multiplying it with the weights and adding a bias. The bias vector size did not change because the number of nodes in the recurrent part is still K. I obtained the next weight. You see, this matrix did grow, as I told you. So I can just split this matrix to the non-recurrent part and the recurrent part. So this part of this is a concatenation. They are just added to each other in the row dimension. So this part takes care of the recurrent part, and this takes care of the non-recurrent part, the output. But and combined, it is a network which creates new states out of the previous state and the new input. And if I need, I can create an output using this new state. It will be a new outcome. So you can represent any type of finite state automata using this. Good, that's the idea of vanilla RNN. And never forget that in a vanilla RNN, when I say input, I mean, I conventionally may mean the external input, but the input to the RNN is not only the external input. It is the external input concatenated with the previous state. That's what it makes a finite state automata. Any questions? I mean, I hope this is not a confusing diagram because it shows every connection and hence every multiplication. I'm going to convert this to a more simplified depiction, which I'm going to be using in the entire course. But if you got any questions, please ask, because these formulas are very simple actually. I'm checking no microphone. So okay, I'll continue. For the sake of simplicity, as I told you, I'm going to switch to a simpler depiction, which Andrew Vengi uses in his course. I mean, Andrew Vengi is a great guy because, I mean, he has good papers. He's from a respected university all the world. They have good papers, but I believe that his most important contribution is about the way of teaching deep learning. He knows how he's got a good team that they work on how to make things look simpler and easier in the world of deep learning. I'm going to switch to that depiction. What is that depiction? So guys, instead of horizontally connecting these lines, I'm going to be using a vertical direction. So the input here, you see, will be the input at below, and the connections from below to the node. So these nodes are here right now. So inside the nodes, as you can see, the weights, summation, and the activation. This ReLU function represents the activation. It is not necessarily a ReLU function. Actually, in vanilla RNNs, we don't use a ReLU function. It is usually something else. I'm going to talk about it. So what I do is I rotate it by 90 degrees in counterclockwise direction. And this is the hidden state. So this representation is only the core part. And I'm going to not use many nodes. I'm going to be using the so-called single supernode representation, in which I have X. So in this line, I have all the connections, and I have the output as a vector. And the feedback here, as you can see, is also vectorial as well. So these lines here are a bit more thick, so thicker lines, and they're actually vectorial. So when you see this, it is this, guys. Don't get fooled, okay? I'm going to be using this because in a couple of minutes, I'm going to unroll the RNN representation in time, okay? Any questions about this representation? I hope not. So this is this representation, everything is the same. So this is the previous state I call Ti. This is the next state, it is Ti plus 1. And what I have is a vector of values, I have the inputs. The formulas are the same, nothing has changed. And the formulas will start with an initial input. What about the initial hidden state? So when I'm providing the initial inputs, I need an initial hidden state, right? What could the value be? I mean, any suggestions? I want to hear from the audience. If you know what it is, you can just say it as well, but then I would ask why. Any ideas? No? What could the initial value for the states could be or should be?
0.
Zeros. Why? Okay. Why? Why zeros? It's a difficult question, by the way. It needs a lot of thinking, in my opinion. Because let's say, okay, please.
It's for the same reason that when you used to define the initial weights in any A and N, you used to define them as zeros or any random numbers for a given distribution.
But you're talking about the weights, right? He's saying that when we initialize things, it's the weights, he says.
Yeah.
Yeah, you're right, but it was the weights. This is a bit more difficult. This is a dynamic system. And actually what we are talking about is, I'm going to give you more clues, the initial condition of a dynamic system. We are talking about using zero origin as the initial state of a dynamic system? Actually, this is a very difficult question, guys. This is related to dynamic systems analysis. If you have taken courses like EE555, it was EE555, I guess. Whatever it is. When you make an analysis of related to optimization or estimation theory or an analysis on dynamic systems, actually, for the convergence of these systems, there are different theories on initial values. I'm not going to cover them mathematically. This is more like a sequence modeling course. But apparently, using the origin as an initial condition is a mathematically and practically better way to do it. The science of it shows, the research behind it shows. There are many studies of it, and I cannot say that it is always the best choice. Maybe for a system, starting from another initial condition will help you to get to a state which is a desirable state. Fast, maybe. I don't know. It could be. However, these systems, the recurrent neural networks, are not transparent, and we don't know the answer most of the time. That's why we traditionally choose it to be zero. So the answer is like, we don't know the answer, and it's traditionally zero is better. Mathematics shows it. That's why we use it, because we cannot comprehend the dynamics of that dynamical system, because this is a dynamical system starting from initial condition. Actually, most of you have taken ordinary differential equations, right? They look like ordinary differential equations. Think about it. In an ordinary differential equation, you start from for example, you are trying to solve an ordinary differential equation. It's a control engineering problem. It's an ordinary differential equation, and you're starting from an initial condition, and you are trying to solve it. That's a dynamical system, right? Actually, this system has no difference. The mathematical representations are quite different, but they can emulate each other. And actually, in 2018, there was a very important paper, a neural ordinary differential equations paper, which attempted to represent RNNs as ordinary differential equations and ordinary differential equations as RNNs. And they come up with very important results, which is something that I'm going to be talking about in this course in the following weeks. So what I'm trying to say is, we will always choose zero, but this is not going to be a very clever decision. It's going to be a conventional decision. A lot of things in AI is today trial and error, because otherwise it won't work. It will be so mathematical and we'll be drowned in it. But until I say the opposite, for most of the systems we are going to cover in the following weeks, this initial condition is going to be zero. It is our start vector in our dynamic system. It's like the initial condition of a differential equation. So it's a bit different than the weights, because we already have weights, and we are going to initialize them using similar methods we did in artificial neural networks like the Saviors or Kaiming Hess, whatever, or Gaussian, whatever. Okay, any questions?
So Jam, do we have any constraints on defining the weights when you are saying that the initial conditions for the states are zero? Or it doesn't matter?
Can you please repeat the question? Do we have any?
Any constraints on the weights? I mean, is there a better way of defining the weights instead of another ways when we are assigning the initial states to be zero?
Initial states to be zero. So you're asking, is there a better way to initialize the weights other than zero? You're asking this, right?
As far as I know, for the weights, there are multiple ways, but is there any connection between the initialization of the weights?
Weights to the, of course there is, because the way you initialize weights is actually changing the dynamical system. He's asking the initialization of weights is, can you hear it, or you just, it's a mental connection. So of course, the answer is of course. I mean, because when you define the weights in some way, you are shaping the dynamical function. That dynamical function is a function of those weights. And it's a hyperdimensional function, because the weights have incredible number of weights. And when you change the shape of the dynamical function, the initial condition will be affected. I mean, the initial condition stays there, but the next step is affected. Of course, yes. That analysis is a common analysis in theoretical mathematics. Is it an analysis commonly done in deep learning? Well, it seems to be no, because deep learning today is mainly data-based. When we cannot solve our problems in today's deep learning, we come up with new data, we augment data, we do transfer learning. We don't work on that stuff. The reason is, it is so untransparent. We cannot understand this. However, the data is, because you just train a system, it kind of works on something, but doesn't work on another thing. What we do is, we get that other thing and add it to the database to make it work. So we are still, treating these things as black boxes, as if it's an alien invention that came to us, and we are trying to understand it superficially. However, regarding your question, yes, absolutely. The weights and the initial condition selection, and maybe after a rigorous analysis, there is. I'm sure the optimization in living things definitely does it. The optimization of weights and the initial conditions in our brain, often it definitely optimizes this. And there could be ways to optimize a certain problem for a certain initial weight as a certain initial state. However, when we are attacking new problems, it is not going to be the way we are going to do this. I hope this makes a question, answer to your question, right?
Yes, thank you, sir.
Okay, so as you can see, what happened is, we were talking about something very simple, that this idiotic formula. I mean, really, it's just a matrix multiplication. I mean, the first grade student, engineering student, did understand this formula. Then we jumped, we just, we beamed up to something very complex, and we just ended up with a conclusion that it is impossible for the AI society in general to understand right now. We can do an analysis, but we can't be sure about it, we said. So this is this deep, guys. With a single vanilla RNN, you can go this deep. But in the following lectures of this course, you're going to see that people in AI started searching for solutions to questions not like these. Can we find a better initial condition? You can. Mathematicians still like it, just like the Neuroloda paper from 2018. It was the best paper in NIPS that year. However, people are searching for more practical questions, searching for answers to more practical questions. For example, can I train it better? What should I do to train it better? During training, my gradients are getting weaker. What can I do to make them stronger? Kind of more engineering-like questions they are searching answers for. And we're going to see it. The nicest example is the LSTM and Schmidt-Huber. Okay, we're going to see it. So I continue if there are no other questions. I'm checking the time. We have about 10 minutes for you, right? Okay, so this was the Supernode representation. What I'm going to be doing it immediately is unrolling in time. If you've ever seen RNNs, you've seen this, I guess. If you've never seen this, it is actually a way to explain why RNNs are sequence modelers. Remember, guys, in an RNN, I feed the input, starting with the initial condition. I get another state. Initial condition, the next state. Then I feed another input with the new state being old now, with the new input. It goes on like this. To depict this, I can unroll the representation in time. So this is the first input, this is the second input, this is the third input. And each time, the next state is being forwarded to the next RNN state. So actually, this looks like a deep neural network with multiple layers. And the number of layers is actually the number of sequence input. How many times I fed a new input to the system. So when you call an RNN 5 times with 5 inputs, actually you're creating a neural network with 5 layers. That's RNNs unrolled in time. And you should definitely understand it. Because when you understand this, you're actually seeing a computational graph of 5 layers. And if you have a computational graph, you can do everything. The first thing you would do is do the backpropagation to train it, right? Because computational graphs, we know how to manipulate. We learned it in the introductory level course. That's why the first thing we do in an RNN is unrolling it, okay? And remember, these were the core parts. If I needed outputs, I'm going to put in the outputs here. And at each input, I would be creating a different output, which is good because I may need multiple outputs. I may need a single output, depending on my type of problem. That's why we are going to use this representation to unroll it in time. And when I unroll it in time, it's going to create a layered network architecture where the number of layers is S being the variable sequence length. So it just satisfied everything. It could create states, memory. It can manipulate variable length data. So this is what RNNs is, and that's how it is capable of implementing any type of finite state automaton. So in this unrolled in time representation, I have K hidden nodes, the number of states, S length distance, S long distance, N long input features, and M long outputs. This is my choice. I've designed the network that way. Okay? Okay, good. So when you just do it, the formulation is still the same. I didn't change it. I copied and pasted from the previous slides. So this is a vanilla RNN unrolled in time. In the depiction, which you can see it as a, it's like an FNN. It is like an FNN, for example. This is no different than an FNN, right? But the important difference is at each layer you are feeding new inputs, but it still looks like a computational graph of an FNN. Because when you unroll it in time, the recurrent connection becomes like a forward connection. It looks like a forward connection, right? So this is something you can train, you know how to just work on. Okay, good. So at this point, you know what an RNN is, you know what the recurrent connection is, you know what the formulas are, you know what the output is, you know how to represent it, and you can how to show it like similar to a feed-forward connection. At this point, before getting into how to train it, I'm going to talk about what different kind of input and output types could be defined using this vanilla architecture in the next hour, if you don't have any questions.